All right, let's dive into this explainer and reverse engineer those everyday optical instruments sitting right now in your biology lab. Look, if you're a biograd student, you're probably spending hours every single week camped out in front of these glowing machines. You put a sample in, you take a reading out, right? But today, we're going to completely transform how you look at that entire process.
Think about it for a second. You push a button on a machine every day, but have you ever stopped to wonder what kind of conversation the light is actually having with your biological samples? It's so easy to treat these instruments like magic vending machines. Insert sample, receive data. But beneath that plastic casing, there's a highly sophisticated physical translation going on. Light is physically interacting with your cells, your proteins, your DNA, and the machine. It's basically just eavesdropping on that conversation.
So today, we are opening up that black box to connect the physical principles of light directly with your biological targets. Because once you actually understand the physics, the real language of light, you can stop just blindly following protocols and start designing some truly brilliant experiments. Here is our roadmap for how we'll do this. First, the foundation, wave versus particle. Second, systems A and B, covering absorption and re-emission. Third, systems C and D, covering waves and quanta. And finally, we'll pull it all together into an optical blueprint. Okay, let's kick things off with part 1, foundation, wave versus particle. Before we look at specific lab tools, we have to establish the shared language of our universe. Light acts as both a wave that ripples through space and a particle that transfers discrete packets of energy. Think of the wave nature like ripples in a pond. It dictates how light scatters, bends, and interferes over space and time. The particle nature, on the other hand, is a lot like dropping specific coins into a vending machine. It's all about discrete packets of energy, called photons, and that dictates absorption, fluorescence, and energy transfer. Mastering this dual nature is literally our master key to pushing biological resolution to the next dimension. Because depending on the specific question you're asking, your machine is going to exploit either those ripples in the pond or the energy of those coins. And here is the beauty of it. Instead of memorizing 10 different machines as completely separate, confusing entities, we can categorize them into 4 logical systems based on how they interact with matter: absorption, re-emission, wave phase, and quantum particles. If you understand these 4 categories, you basically understand the entire lab. Moving right along to Section 2, Systems A and B, Absorption and Re-emission. These first 2 systems are all about the direct action and reaction between light energy and your molecules. In System A, we focus on absorption. Take the classic UV-Vis spectrophotometer. It uses electron transitions to measure the concentration and purity of DNA or proteins based on the specific colors of light they absorb. Think of your molecules like highly picky toll booths. They will only absorb light particles, photons, that have the exact precise amount of energy needed to make their electrons leap to a higher state. By measuring what light doesn't make it through the sample, we use the Beer-Lambert law to calculate exactly how much of that molecule is floating around in there. Now let's compare that to FTIR and see how this builds when we switch our light source. While UV-Vis looks at high-energy electron leaps, FTIR, or Fourier transform infrared spectroscopy, uses lower-energy infrared light to look at molecular shaking or vibrations. So instead of making electrons jump, FTIR acts like a tuning fork that resonates with the physical springs between atoms. This is awesome because it allows you to deduce the exact chemical structure, like whether a protein is folded into an alpha helix or a beta sheet, literally just by analyzing how it jiggles. Also sitting in System A, we have near-infrared spectroscopy, or NIRS. This one acts kind of like a pair of X-ray glasses by utilizing what we call the biological window. See, in a specific near-infrared range, the absorption from water and hemoglobin drops off drastically, and scattering is minimized. This is huge because it lets you shine light through a deep, dense forest of human tissue to non-invasively measure things like oxygen saturation or even brain activity. Okay, let's shift gears to System B, where we look at light re-emission and molecular behavior. Rather than just seeing what's absorbed, we are looking at the light that bounces back or transfers. A prime example here is FRET, or Forster Resonance Energy Transfer. FRET allows us to measure biological interactions happening at incredibly, unbelievably close distances, like between 1 and 10 nanometers. The crucial takeaway here is that FRET isn't just a microscope technique. It's a nanoscale ruler that detects when 2 proteins are physically interacting in real time.
Think of it like two friends in a really crowded, noisy room. One absorbs energy, but instead of shouting it out or emitting a photon, they just whisper that energy directly to their friend right next to them. If they move even a tiny, tiny bit apart, the whisper fails. Because this energy transfer drops off at the sixth power of their distance, it acts as an incredibly precise ruler for protein-protein interactions. And to wrap up System B, we have SIRS, or Surface-Enhanced Raman Scattering. Normally, Raman scattering, which reads the unique vibrational fingerprints of molecules, is incredibly weak. It's super hard to detect. But SIRS solves this by using metallic nanostructures, like gold or silver. When light hits these metals, it creates a local surface plasmon resonance. Basically, it acts as an extreme amplifier, a microscopic megaphone that takes the extremely faint fingerprint of a single biomarker and boosts its signal by millions, sometimes billions of times.
All right, let's jump to Section 3, Systems C and D, Waves and Quanta. Out here, things get slightly more abstract because we're utilizing pure wave behavior and quantum limits. In System C, we're exploiting the ripple-like wave properties of light. Optical coherence tomography, or OCT, essentially acts like a 3D echo, using the overlapping interference of light waves to map out deep tissue structures non-invasively. It works exactly like sonar or an ultrasound. But because light is way too fast to measure its round-trip time directly, OCT measures the interference pattern when the reflected wave overlaps with a reference wave. This gives us stunningly precise micron-level cross-sections of things like the human retina.
Meanwhile, also in System C, we have circular dichromism, or CD. This actually twists the light wave itself. By using circular polarization, imagine a wave spiraling forward like a corkscrew. CD perfectly captures the delicate folding and unwinding of proteins in real time. Here's why. Because folded proteins have chirality, or a physical handedness to them, they will absorb a right-twisting light wave slightly differently than a left-twisting light wave. Measuring that subtle difference lets us track melting temperatures and structural stability, all without destroying the sample.
But what happens when you want to measure the ultimate biological limit, down to just a single isolated event? Like, what if you are looking for the absolute faintest possible whisper of a cell under oxidative stress? Well, that brings us to System D, Photon Counting. This is a purely quantum measurement technique that leverages the photoelectric effect to literally count individual, invisible particles of light. Think of it like trying to catch and count single raindrops in the middle of a massive storm. By catching a single photon, knocking loose an electron, and triggering a massive avalanche of secondary electrons to create a measurable pulse, this technique achieves the absolute ultimate edge of sensitivity for things like biophoton emission and single-molecule dynamics.
And finally, Section 4, the optical blueprint. So now that we've decoded all the jargon and compared the techniques, let's put it all together into a practical master plan. If you know what you are looking for in biology, you can instantly deduce which physical property of light you need to exploit. Are you looking for single-molecule binding? You're going to need the re-emission of System B, like FRET, or the quantum counting of System D. Do you need to check the secondary structure of a protein? You rely on the vibrational resonance of System A's FTIR, or the wave phase of System C's circular dichroism. Or maybe you want to see deep into tissue. Then you exploit the scattering properties in System A's NIRS or System C's OCT. What's really, truly incredible about this integration matrix is that it proves your biological question will always dictate the physical equation. You don't need to be intimidated by the physics anymore. The physics is literally just the medium. By understanding that vibration and twisting reveals structure, windows and scattering reveals depth, and counting particles reveals the extreme limits, you completely elevate your biological resolution to the next dimension. Armed with this new blueprint, the black boxes in your lab are officially open. You now know the exact language these machines are speaking. So the next time you sit down at the lab bench to run a sample, how will you choose to converse with the microscopic world? Will you use ripples, or will you use coins? Thanks so much for joining me on this explainer, and I absolutely hope this transforms your next big breakthrough.